Okay, we can get started. I'll record this. Okay, since your midterm is actually next week, we're not going to go to tutorial 4 just yet because it's not actually covered in your midterm. It's all just going to be on the cycles and all the other thermodynamic stuff. So none of the state counting content. So yeah, we'll try to finish off the third tutorial set today because that's more relevant to what you need to know. Alright, so let's start with question 6 for tutorial 3. Is it clear? The camera's a bit blurry. Hello. Alright, cool. Alright, so use the Gibbs-Duhem relation in the entropy representation, derive the form of the chemical potential for an ideal monatomic gas. Okay, so what that basically means is that you want to write out the entropy representation, so starting with ds. But then for the so 1 on t, du, and then plus p on t dv minus mu on t dn. So basically just the internal energy definition, but then I take entropy as the subject and divide it through by T, temperature. So this is equation start. And a separate equation is the entropy written as the Euler integral. So 1 on T U plus P on T V minus mu on T N. And this is equation double star. The one point of confusion, don't assume this is not an integral. Like you didn't get equation 2 by integrating the first equation. The second equation comes from Euler's homogeneous function theorem. Did you learn that in class?
We did the proof of it, but we didn't actually it wasn't called the homogeneous function theorem.
Okay.
But they didn't prove it.
Okay, so you know where it comes from. Okay, cool. Then I won't go through it. Okay, so in that case, we'll differentiate the Euler relation. So differentiate the second equation. So diff star star. And we get just ds is equal to, and then just differentiate each of these by chain rule. So you get d 1 on t u plus du 1. So I should make these u's bigger. That's still the extensive u, not the intensive u. Plus d p on t v dv. Okay, so you just differentiate the second equation, and now you equate this to the first law of thermodynamics, so the first equation star, because both of them are ds, so technically the right-hand side should equal each other. And you can see that this term will cancel out with this term will cancel out with this term, and this term will cancel out with this term. So you actually just end up with 3 terms left. So 0 is equal to u d1 on t plus v dp on t minus n mu on t. So this is the equation you should end up with after equating the 2. And now we're just going to downgrade these to intensive variables, so we can divide through everything by n, and left-hand side is 0, so it's not going to care. So we get a lowercase u, a small v, and this n just disappears because we divided through by n. So now we have these in specific quantities. And now we can just sub in the ideal gas equations for both the internal energy and the volume. So we know U is equal to 3/2 kT, and P little v is equal to kT. So we just substitute these two into there, and we eventually get 0 is equal to 3/2 kT d1 on t, and plus kT on p dp on t minus d mu on t. Yeah, so after substituting the ideal gas equation, you should get this. And now we just want to define some like arbitrary variables. So rather than carrying around all this temperature, we're going to define 1 on t to be called capital X, and p on t to be called capital Y. This doesn't really matter. It just makes things a bit neater. So once you do that, and then take the d mu on t to the left-hand side, you'll see what you get is d mu on t is equal to 3k on 2, 1 on x dx plus k on y dy. And now that should be really easy to solve because it's just two integrals of one over the variable, so it just be two logarithms. So then this tells me the chemical potential at some pressure and some temperature is given to you by the initial chemical potential divided by T0 times by T plus KT log of P on T to the 5/2. I skipped a couple bit of algebra over here, but really it's just if you evaluate this integral and then taking you get mu on T is equal to the result of this integral, but then just taking the temperature to the right hand side, that's why you get a T on the numerator here. And this log is just combining these two together since they both involve T, so it will just be P on T with like a slightly weird power. But yeah, so that's the answer. So that's how you get the chemical potential in terms of some pressure and temperature. Yeah, any questions? No, all good.
Sorry, can you explain again on how you derive the final answer, like the mu naught over T naught, where is that coming from?
Oh, because when you do the integral, you get like a constant term. So I'm just saying like the mu naught and T naught is like the initial condition kind of thing. Yeah. Yeah, you can call this whole thing like just C if you want. It's same thing. Question 7. Derive the Maxwell relation, including those for chemical potential and the number of particles for the Gibbs potential. So Maxwell's relations are basically comes from Schwartz theorem. It's like a fancy way of saying your second derivative order doesn't really matter. So if you differentiate between between two variables, which one you do first is not important. So we know for the Gibbs potential, G is defined as the internal energy Legendre transformed. So we want to plus P on B to swap the variables P and B in the internal energy and then swap the T and S Yep, so in that case, we can then just take the differential of G, and it will be du plus pdv plus vdp minus tds minus sdt. So as you can see, the pdv and the tds is going to end up canceling out with like the terms in du. And you end up with a mu dn, that's the only thing that survives from du term. So these two cancel out with du, and all you're left with is vdp minus sdt plus mu dn. So mu dn is the only contribution left from the internal energy. Okay, so now if you compare this expression for the total differential of dg with, like, if we were completely agnostic about the function g and we only know it as a like a general function of 3 variables, then if we just imagine this dg, dt, and with the other two constant, p and n, dt plus dg, dp, t and n constant, dp plus dg, dn, tnp constant, dn. Then you can just go match the coefficients and say, okay, this one's the coefficient of dt, so that must be entropy or minus entropy. This one's the coefficient of dp, so that must be volume. And this one is the coefficient of dn, so that must be the chemical potential, mu. Now that you know these three, so you have this association with them, then you can just go ahead and derive the Maxwell's equations, relations, right? So the first one, the way you do this is just, okay, you take, let's just start with this one. So you get dg, dt of p and n. And you pick one of the variables that you want to differentiate with, like, again, with respect to. So it could be one of the p or the n, but only pick one. So let's just go with, let's say p for now. So at the front you get d, dp. And now you're holding t and n constant for this partial differential. Is it clear on the Zoom? Yeah, it looks right. Yeah, so now that you got this written down, then you can just immediately substitute in this entropy term. So you get minus ds dp of t and n. So if I sub minus s in there, and the rest of it just sits in here. And that's what you get for this second derivative. But now I use like the idea that it's symmetric, so you can just swap the order. So this is also equal to, if I do it the other way around and instead have d dt holding p and n constant, and then times by dg dp holding t and n constant. So these two are identical to each other, but this one is now reading off the coefficient for this, which is the volume. So then now this one is equal to dv dt holding p and n constant. So your Maxwell's relation is relating these two terms to each other. So taking advantage of the fact that these second derivatives are the same, you now know dv dt is the same as ds dp. And you just go about this the exact same way for all of them. So just pick the next partial derivative that you want to do. So dg dp, for example, holding t and n constant. Pick another variable down here. Let's do n this time. So you get ddn of t and p constant. So then dg dp is v. So this is dv dn with t and p constant. And then the other way around, do dg dn, dg dp first of t and n, and dg dn of t and p. dg dn t and p with t and p constant, that's mu. So then this one is equal to d mu dp of t and n constant. So it's the exact same game that you're playing, just swapping out these second derivatives. And this is your second Maxwell's relation. And there should be another one. So hold on, which one did I not do yet? So I have now, let's see. I've done dgdn and dgdp. So I'm missing dgdn and dgdt. So the dgdn holding t and p constant, and out of front I got ddt with p and n constant. So that is d mu dt. And constant. And that's equal to the other way around, so ddn of t and p, and then dg dt of p and n. And that's equal to dg dt is the entropy, so that's minus ds dn t and p. And that's the last one, so that's 3 of them. Yeah, makes sense. Yeah, and then you can do the exact same thing with the grand potential. So that's a capital omega. It's pretty much the exact same game. So I'm just gonna write it up, but I'm not gonna do it step by step again because it's the exact same way you do it. So you have the grand potential, which is for your grand canonical ensemble, defined as the temperature, volume, and mu. So this will just equal to internal energy minus Ts, but rather than Legendre transforming for PV, this time I want mu, so then I need to minus mu n. So just slightly different to Gibbs potential by having mu n instead of PV here. And yeah, you do the exact same thing, then you get d omega is equal to minus p dv minus s dt and minus n d mu. Yeah, so you can associate this as d omega dv s, and this is d omega dt vn, v mu, sorry. These are mu chemical potentials now. And number density, the number of particles is d omega d mu. So if this was in the exam, the 2 questions came one after the other, you can literally just go back to the other one and substituting mu for all the places that you see n, and it will still work. But okay, if you do it properly, then yeah, just go d omega, which one do we do first? Let's just do v with s and mu constant. Sorry, not s, st. And then pick another variable to differentiate in front of it. So out of t and mu, let's do d mu. So this one's holding t and v constant. So this will be dp d mu of t and v. Same as ddv of t and mu, d omega d mu t and v. And d omega d mu t and v is the number n, so this is dn dv t and mu. And yeah, I'll leave the other 2 for as an exercise. There's not much there to do here. I might have missed some minus signs here. Don't know if this is going to come up in the exam. Wouldn't be the craziest question to ask, but probably not the missing because there's not a lot of time to ask everything. All good with this? Yeah. Okay, and then we have an actual thermodynamics question now. Question A. What is the change in Gibbs potential upon mixing two ideal monotonic gas isothermally? So you're mixing them isothermally, and you can imagine this system as two different gases of the same like kind of characteristic, but like two different tags. So tag one of them gas 1 and the other one gas 2. So just tag them and put them in a box and start them with a partition in the middle. So you have gas 1 in here and gas 2 in here, and they were just happily flying around. Gas 2 crosses. But these are just tags. Like at the end of the day, gas 1 and gas 2 are the exact same thing. So once I break this partition and let them mix together, I technically would have no way of distinguishing the two, except for the fact that I arbitrarily assume that I have tagged them somehow, so I do know which one's which, but chemically there's no difference. And you want to ask, does the free energy increase or decrease? So is delta G positive or negative? Okay, so to start this, you just write down G, U plus PV minus TS. So now you use a very dodgy assumption, not dodgy, but like it's a very special assumption, because here we're looking at a monatomic gas mixing. And nothing fancy is going on. There's just two like kind of group of gas going around with each other. So technically this system from far away, or like even just looking at it mildly, it's pretty homogeneous. So we can assume it's a homogeneous gas. And in that case, you can sub in for U. U is then satisfying the Euler's relation, Ts minus PV plus mu n. So you can sub this into this expression. So this is only valid if it's a homogeneous gas. So it's not a general thing that you can do with any thermodynamic system. So if you have like fancy things going on here, then that's not going to work. But in this case, we just have one type of monatomic gas floating around. So this is perfectly fine. So once you sub that in, then like everything cancels out except for the mu n term. So you end up getting G is just equal to mu n under this assumption, under homogeneity. I'm just gonna rub this out because I need more room. Okay, so now under this homogeneity assumption, I now have two, not exactly separate, but two like starting points for the Gibbs free energy. And I can differentiate both of them. So let's differentiate this one first. So dG is in this case mu dn plus n d mu. And in general, we can now also differentiate the actual Gibbs free energy expression. And we can do this just like we always do. So dG is du plus pdv plus vdp, blah, blah, blah. But then you sub in the internal energy. So this becomes the simplified version. So minus sdt plus vdp plus mu dn. So yeah, these are the two differentials. And again, I equate the two because technically they're both differentials of the Gibbs function. So under these circumstances, they're the same object. So I equate the two sides. I cancel out the mu dn, and then I end up with an expression for n d mu is equal to all this. So n d mu is equal to minus s dt plus v dp. So this is like the result of us considering a homogeneous gas. Okay, and now let's take it back here. And I want to reduce this to a specific value equation. So I just divide the n across the right-hand side and reduce these s and v into specific quantities. So I get d mu is equal to little s dt, sorry, minus little s dt plus little v dp. And now I can integrate this to get the chemical potential for a particular homogeneous gas. So mu as a function of Tmp is going to equal some constant, the initial conditions, I'm just going to call mu naught, mu 0, plus the integral of this whole thing, minus s dt plus little v dp. But we're also considering, in the question, we also mentioned that this whole thing happens isothermally. So put in an isothermal condition and we can delete this dt term because that's not going to contribute anything. That's just going to be 0. So all we're left is a VDP integral. So our chemical potential is equal to mu naught plus integral from some pressure, let's call it P naught, to the pressure that we're interested in, say P, I'm just going to P, integral V dP dash. But that dash is to distinguish between like an integration variable and the actual physical pressure that we care about. So this is mu at the particular pressure P. And this P naught is a reference pressure. So you can set this to whatever you want. I think the common thing is to do is set P naught to 1 bar, but really just saying that going from some reference pressure to the pressure that you care about, this is the expression. And now it's a monotonic ideal gas, so V is just, little v is just kT divided by P. So this is mu naught plus integral kT divided by P prime dP prime from P naught to P. So mu at some pressure is equal to mu naught plus kT log of P divided by P naught. So this is the first step. We first need to get the chemical potential as an expression of pressure. Okay, I'm going to use another board down here. Okay, now that you got the chemical potential, let's go back to the Gibbs function, the Gibbs potential. So for the homogeneous case, we said G is equal to mu n. That's for one type of gas. Now in this problem, we have essentially macroscopically only one type of gas. But then remember, we arbitrarily tag them 1 and 2. So let's just pretend for now we have half of them as species 1, half of them species 2, even though they're the same species. So I'll write the Gibbs potential pretending like I have 2 species. So sum over the species. So this is equal to mu1 n1 plus mu2 n2. Yep, so now to find delta G, we're just going to find what's the initial Gibbs potential and what is the final Gibbs potential using this expression. So let's do the initial first. So G initial is equal to N1, which we don't really know and we don't really need to care, is N1. And then we sub in the expression for mu1 from what we just derived. So you got some initial mu naught dash 1, that's the label for the species 1, plus kT log of P divided by P naught. And then exactly the same thing for species 2, except we have mu naught 2 instead, plus kT log of P on P naught. Now I've used the same P here because physically, if I had the same amount of gas in these two partitions, and I let them do their own thing and they equilibrate and they find the equilibrium pressure, then if they're the same gas and the same amount of them in both partitions, then it's pretty natural to think that the pressure in here is going to be the same as the pressure in here. So that's why we can label both of these pressures as the same P, because initially they should be the exact same pressure. Now, the final Gibbs potential is pretty much exactly the same thing. We know 1 plus kT log. Except here, when we need to decide what is the final pressure, what do we put for the final pressure for gas 1? Let's just call it P1 here. But how do you physically understand P1 is that if I ignore gas 2 for now, I only have gas 1. And I break this partition. So initially, so for gas 1, the initial pressure is just P. And now I break the partition and let them float around and let them equilibrate again. Then in absence of gas 2, they're gonna probably like look something like this, like spread out across the box homogeneously. So then the final pressure P1, that's going to be less than the initial pressure P because you now have a much larger volume to occupy. So all the gases are spread out and you have less gas pressure internally. And the same thing for P2. P2 initially all come together on the right-hand side of the box, and now they're like spread out homogeneously across the entire box in crosses. So the final P2 is also less than P. But we have both P1, P2, both gas 1 and gas 2 together in this box, and they reach an equilibrium. We have the same number of particles, the same total volume, which is like the entire box in itself. So then the final total pressure, total P, which is P1, PF, P1 plus P2, should just equal the initial pressure P. That's like, this is probably the hardest part to get your head around. If you can understand that the final total pressure is the same as just the final individual pressures added together, then you're fine. So this is what they call partial pressure. Idea is just that we treat each gas individually and then ignore the other one while we just consider this that one species, even though they're the same. So in that regard, then we get this one plus N2 mu naught 2 plus kT log of P2 on P naught. So that's our initial Gibbs energy and that's our final Gibbs energy. And they're pretty much exactly the same as each other, except for I have now a P1 here and just a P here. So now if I take the difference of the two, so delta G, which is G final minus G initial, all of these mu naught 1s and mu naught 2s, they're going to cancel each other out. So all we're going to have, and this log of 1 on P naught and log of 1 on P naught are going to cancel each other out. So all we're going to have left is N1 KT log of P1 on P plus N2 KT log of P2 on P. So all the other terms are cancelled out, and this is all we have left. And as we said before, because of the partial pressure argument, P1 and P2 are both less than the initial pressure, big P. So this ratio is less than 1, so this log term will make it less than 0. This ratio is less than 1, so this log is also less than 0. Everything else is positive constants, so this whole thing is less than 0. So we actually went to a lower Gibbs energy state after mixing. And that makes sense because you minimize Gibbs free energy when you want to reach equilibrium in any system.
Is there like a general intuition as to what the Gibbs free energy represents?
No, it's just another way of writing energy where your natural variables are different to the internal energy. Yeah, but no, like at least I don't ever try to think about this intuitively. Question 9 is an open question that I frankly have no idea what is going on. And yeah, I'll let you know if I come up with anything, but I looked at it for a while and I couldn't come up with anything like useful to say. Okay, then let's go to question 10. Okay, so question 10 is very similar to questions we did before. So similar formalism that thermodynamic potential can be applied to the entropy representation. These functions are commonly known as the Planck or the Massieu functions. Derived the Massieu function corresponds to a barostated and thermostated system. So barostated and thermostated just means you want to have pressure and temperature as your control variables. So question 10. So since the question hinted that we have to start with the entropy representation, that means rather than writing down internal energy as a function of entropy, volume, and number, we write down the entropy as a function of internal energy, volume, and number. So that's just a fancy way of saying that we now swapped internal energy with entropy to look at entropy as the function of interest. And yeah, the differential form you've all seen 100 times before, so it's just 1 over t du plus p on t dv minus mu on t dn. So it's just the first law of thermodynamics where you take the entropy to the swap entropy with internal energy and divide everything through by T. Okay, so now we take this as our starting point, and we now have volume and number as our volume and internal energy as our variables, which is not what the question wants. We want a barostated and thermostated system, so we want to perform a Legendre transform. And we want to Legendre transform U to temperature and V to P, so we can get pressure and temperature stated. So in this case, we define this new function as the Massieu function. So I have no idea what this Greek letter is called. Looks like Pac-Man. Is equal to S minus U on T minus PV on T. So it's a bit different to the normal Legendre transforms you see. Like PV is what you normally expect when you do this, but because entropy representation, you always carry around this 1 on T with you. And the U transformation, you can think of as like the coefficient 1. So this is like 1 times U over T, Legendre transform. So it looks a bit odd, but it always looks like that for entropy representation. Okay, so now we just perform this Legendre transform and see what it looks like. And so we take the derivative of the Massieu function, and that's equal to, oh boy, okay, ds minus d1 on t u plus minus 1 on t du minus d p on t v minus dv p on t. Yep, and okay, I'm just going to do another line, and then you keep differentiating that, so you get ds minus 1 on t. Sorry, this is minus 1 on minus, so this is plus 1 on t squared dt and u on top, and then minus 1 on t du, and minus 1 t du plus p P on T dV. I'm doing it in the wrong order, but I'm just gonna start again. I think I did them in the wrong order and now I'm confusing myself. Alright, I'm just gonna write this whole thing out. So including ds, extending ds using this. So I get 1 on T du plus P on T dV minus mu on T dn, so that's all of ds. And then I get minus 1 on T du plus u on T squared dt minus P on T dV minus V on T dP plus PV on T squared dt. Sorry, went off the page a little bit. Yeah, and then we can cancel a couple of terms. So this term cancels out with this one. This term cancels out with this one. And that's it. So those are the terms that are surviving. So the surviving terms you get equals minus mu on T dn plus u on T squared dt minus V on T dP plus PV on T squared dt. So this is your fundamental equation of a sort for Massue equation. You can simplify this. So this is, it looks a bit weird because you picked up an additional term that was like proportional to T squared, so it looks a bit funny. So if I work this out, so if you take that equation, you can simplify it down by defining some variables that probably would be useful to define up here. So define beta to equal 1 on T. And you also want to define pi, and not the math pi, not the number, is P on T, and nu to be minus mu on T. So once you see that, then you can see d beta is equal to minus 1 on T squared dt. So this could be put into here to get you get rid of this T squared. It looks a bit weird. And then d pi is equal to dP on T minus dt p dt on T squared. So these two terms collected together, rather than having dP and dt separate with this T squared and PV everywhere, it's actually just d pi. And then the last one's easy. So d nu is just equal to minus d mu on T. Oh, sorry, no, you don't do d mu at all because you just sub it in. So then putting these definitions in here, your fundamental equation for Massue equation is a lot simpler. So it's just equal to nu dn minus u d beta minus v d pi. So this is the Massue equation. And now for the second part question, you also have to relate this to one of the more commonly known thermodynamic potentials. So you can stare at that forever and try to figure it out, or you can just cheat like I did. So you guess an answer, the ansatz. The ansatz in this case, let's just say, okay, what if the Massue function is something like g on t? So G is the Gibbs function divided by temperature. Does that make any sense? I don't know, maybe it does. But let's look at how does it work. So if I want to check this relation, I know what this thing is, which is that. So now I just have to check the right-hand side, see if dg on t looks anything like that. If it does, then I can relate my sweep function to the Gibbs potential that way. So right-hand side dg on t, and that's equal to 1 on t dg minus g on t squared dt. And then we use the general expression for G. We can't use the homogeneous gas approximation here because this is just some thermodynamic system. We can't make any assumptions. So just U plus PV minus TS. Okay, and then dG is minus S dt plus VdP minus mu dn plus mu dn. So substitute these two things into dg on t. We get dg on t is equal to very ugly things minus s on t dt plus v on t dp plus mu on t dn. That's the first term. And then for the second term, you have minus u on t squared dt plus pv on t squared dt plus s on t dt. Is that the second term? So this plus s on t dt cancels out with this minus s on t dt, and nothing else cancels out. So we just write down what's left. So let's write in a slightly different order. Mu on t dn plus minus u on t squared dt plus v on t dp plus pv on t squared dt. So this is the g on t. And if we compare this to what we got for my sweep function before we put the substitutions in, you can see that it's exactly the same. It's just out by a minus sign. So this is actually equal to minus d. I really got to learn what the name of this letter is. But yeah, so these two are read by a minus sign. So then we can come back and say, okay, cool. My sweep function is actually just the minus of the Gibbs potential divided by temperature. Yeah. Yes, up to some constant. Yeah.
Like most of the potentials just kind of differ by a constant anyway, so like does that matter? Or...
Yeah, it doesn't say a lot.
Right, yeah.
There are a lot of them. I think there's like outside the four normal ones like internal energy, enthalpy, Gibbs, and Helmholtz. I think there's like 3 more out there, or 4 more out there. One of them is this Massue function, and then there's some other ones. They're just kind of there because in a physical application, you might have different like physical handles, like you might be able to change the pressure for your experiment, but you can't change the volume. Then it makes more sense to use the Gibbs potential rather than using internal energy. But at the end of the day, you're still measuring the same like kind of energy like quantity. So it's not that different. So it really just depends on what is most natural for your problem, and you pick that particular potential to use. Yeah, but they're not meant to be that different fundamentally.
Do you get the other potentials just by doing like different Legendre transforms to the entropy representation?
Yeah, pretty much. So yeah, the 4 weird ones are the entropy representation transforms, and the 4 normal ones are the internal energy transforms. Yeah. Okay, yes, so that's it for tutorial 3, but do revise your questions for the midstem, especially those cycle questions with the efficiency derivation and like heat in, heat out stuff. Paul Kermey is not known to be the most innovative kind when setting exams, which is good for you because if you look at the past papers, you can get most of what's coming. So yeah, do practice those. Yeah, and feel free to email me if you have any questions.
Is our next tutorial on tutorial 4 questions?
Yeah, I'm going to do like a mix of 4 and 5 to catch back on pace. Yeah. No, it's not going to be any counting states and stuff like that. Just going to be thermodynamics. Okay, see you guys next week.